Just as sometimes we need to convert from polar to rectangular, sometimes we're given coordinates in rectangular form and we need to convert them to polar form. So here's how we do that. I want to take these rectangular coordinates and put them into the form r comma theta. The question is, what do I need? What is the mechanism I need to do that? It's not quite as straightforward as going from polar to rectangular. We need to make a couple of observations. One of them is that x squared plus y squared equals r squared. That's the equation of a circle. And we have x and y. We have -4 and 6. So I can take x and square it and add it to y squared, and that's going to give me r squared. So let's see, that's going to be 16 plus 36 is r squared. Add those two together and you get 52 equals r squared. So r equals the square root of 52. Now, when I write my coordinates, I'm going to have the square root of 52 for my radius, and I need to figure out what my theta is, what my angle is. We're still going to use the fact that x equals r cosine of theta and y equals r sine of theta. But instead of plugging values in directly, because we don't have r and cosine, we're looking for r and cosine. So I'm going to rewrite these as x over r, dividing both sides by r, x over r equals cosine theta, and y over r equals sine theta. And then I'm going to make the observation, let me split this up a little bit here. I'm going to make the observation that tangent of theta is equal to sine of theta over cosine of theta. And in this case, that's y over r over x over r. I can either use that shorthand, that shortcut, or I can rewrite this as y over r times r over x and cancel the r's there. Either way, I end up with this being equal to y over x. Well, again, I have a y and I have an x. I have 6 for my y and I have -4 for my x. I get -3/2. But that's the tangent of theta, -3/2. To find theta, I need to take the inverse tangent of -3/2. And that's, tangent is not 3/2. Tangent of some angle is not 3/2 ever for a common angle. So that means this is calculator work. But I am going to need to make this observation. All students take calculus. I'm working with a tangent. The tangent of some angle is negative. So everything's positive here. Tangent is positive here. Therefore, tangent is negative, which is what I want this time, in these two quadrants. So either my angle is going to be in quadrant 2 or in quadrant 4. This is fairly involved, so please be patient. There's a lot to consider here. The first thing I'm going to do is take the tangent inverse of -3/2 on my calculator, and then we're going to determine from the result which quadrant my answer is in, right? So I'm going to do this arithmetic off screen on my calculator. If I take the tangent inverse of -3/2, I get approximately -0.982793. So 98279. Now, where is that? Well, the tangent inverse can only be discovered, talked about, played around with in these two quadrants, right? That's where we decided tangent inverse, that's where we decided the tangent had an inverse, was between -π/2 and π/2. -π/2, π/2. So where is this angle? Well, it has to be in one of these two quadrants, and yet it also has to be negative, so it has to be in quadrant 4. So I'm going to draw what I think is a fairly reasonable sketch of where I think this angle is, recognizing that -0.98 is really almost -1. And if you compare that to an entire half cycle, right, 0 to pi, in terms of how many radians that is, negative 0.9, it's about a third of the way between here and here. So this angle should be about here. It's not a nice pi over 3. It's not, doesn't have a reference angle of pi over 3, but it's reasonably close. Now let's take a look at where our original point was. This is the point we're trying to convert, negative 4, 6. That point is in quadrant 2, negative 4, 6, maybe about there. So we need to find another angle whose tangent is negative 0.98279, but that's in quadrant 2. Fortunately, tangent has a period of pi, so all we need to do is add pi to this, and we have this angle here. So if this angle, let me get the right pen here. If this angle here is negative 0.98279, then that's my reference angle. 0.98279 is my reference angle. So I need a reference angle here of 0.98279. So it's going to be about there. I missed my point a little bit, but the reference angle is the same, right? And I'm kind of trying to show that that angle will go through that point, or that terminal ray will go through that point. And I need this reference angle here. This angle here is negative 0.9. Let's just call it negative 0.9 for argument's sake. This angle here is negative 0.9. The reference angle here is 0.9. So the reference angle here is 0.9. I need to know what the name of this angle is. So I'm going to take pi and subtract 0.9. I'm actually going to take pi and subtract 0.98279. So I need to make sure I still have 0.98279, negative 0.98279 on my calculator, and then I can take pi minus this value, or if I still have negative 0.98279, etc. on my calculator, I can just add pi. So that's what I'm going to do next. And when I do, I get 2.158798. So 8798 would be rounded up to 880. 880 to 5 decimal places. Like I said, recently I'm on a kick of 5 decimal places. I'm going to say use 3. I'll probably mention this in class. 3 is kind of my bare minimum. I like 5. It just feels really accurate without being completely cumbersome to write down. Anyway, 3 decimal places is fine, but then that would round this to 0.159. Do be careful that you round correctly. So the angle that I found here is 2.15880 radians. I've been working in radians this whole time, and that is theta, right? I did this tangent inverse to find theta. So now that I have my theta and it's in the right quadrant, the same quadrant as my original point, I can write that theta is 2.16, let's call it 2.159 radians. And that's my answer. It was a little more involved, but I can convert from rectangular coordinates into polar coordinates by following this process. Now, let's see if we can tidy this up a little bit. The radius isn't too hard. You just recognize that x squared is plus y squared is r squared, and you can literally plug these values in. So finding r is just a matter of doing a little bit of arithmetic. Remember that that's the formula you need, and then do the arithmetic and come up with your r value. So here's the formula you need. I'm going to write it as r equals the square root of x squared plus y squared. And the reason that I'm changing the way it's written is that for me, when I look at these formulas, I want to be able to look at this, x comma y, and say, oh, I want r and theta. How do I get r and how do I get theta? Well, here's how I get r. Plug these values in, take the square root. So I'm actually going to keep that version, and I'm going to erase this one, and I'm going to move this out of the way slightly, I think. There it goes. And now I'm going to look at how do you find theta. Well, we did all this work, but we don't necessarily need to do it every single time. Notice that this was, where did I go? Y over x, right? We found y over x. We found that tangent of theta was equal to y over x. And then we plugged those values in, and we took the tangent inverse. Well, this was my y over x. So theta, this thing that I found down here, can be found by taking the tangent inverse of y over x. So there's your formula for finding theta. The thing with theta is you have to be careful to make sure you're allowed to find it. Where are you allowed to find it? Where is it actually? What quadrant is it actually in? Okay. When the calculator found theta for me, I knew it had to be here because the calculator can only find tangent inverse if it's in one of these two quadrants. It has to give me tangent inverse in either quadrant 1 or quadrant 4. I needed it to be in quadrant 2, so that's why I had to do this other arithmetic. So here are your formulas for converting from Cartesian coordinates or rectangular coordinates to polar coordinates. And we've done an example. We used an example here, this point right here, to make the point that these are how you this is how you find these values. This little box up here now is just kind of a summary. All right. So now that we've talked about that, we're going to go on to how to transform whole equations between polar and rectangular, from polar to rectangular and rectangular to polar form. That's our next video. I'll see you over there.